Have you ever really thought about how your morning coffee cools down? Or how the heck a super powerful computer chip doesn't just, melt? Well, it all comes down to a single, really powerful, fundamental law. Today, we're going to pull back the curtain on the heat conduction equation. Think of it as the ultimate recipe that describes how heat flows through, well, pretty much everything.
So the very first big idea we need to get our heads around is this. Heat isn't just a number. It's not static. As the book says, it's a vector. That means it doesn't just exist in a spot, it moves with a purpose, and it always moves from hot to cold. That directionality, that flow, is what makes this whole topic so dynamic and interesting.
And this is a perfect way to picture that difference. On one hand, you've got temperature. That's a scalar. It just answers the question, how hot is it? So this potato is 50 degrees Celsius. Simple. But heat transfer, that's the vector. It answers how hot and which way is the energy going. Knowing that 80 watts of energy are leaving that potato every square meter, that tells you a story. It tells you it's actively cooling down right now. Okay, so if we want to describe this flow, we need a way to, to map it out. And that map needs coordinates. Not just in space, like left and right, up and down, but also across time. Let's tackle the time part first. You see, sometimes a system can reach what we call a steady state. So imagine it's winter, and your furnace has been running for hours on end. The temperature inside a wall, at any specific point, isn't really changing anymore. It's still cold on the outside, warm on the inside, but the flow of heat has stabilized. Everything's in a nice thermal balance. But honestly, most of the time, things are in a transient state. This is when temperatures are actively on the move. Think about an engine warming up, or that coffee cup cooling down. In these cases, the temperature at any point depends not just on where it is, but also on how much time has passed since you started the clock. So, we've got time sorted. Now we need to talk about space. We need coordinates, an address, to describe where the heat is. And this is a huge deal, because we have to decide, is the heat basically flowing in a straight line, like a 1D problem, or is it spreading across a surface in 2D? Or is it moving through a complex 3D object? Now, let's be real, a full 3D problem can get messy and fast. So the real art and science of engineering is knowing when you can simplify things. When is it actually okay to look at a complex 3D object and just treat it like a simple one-dimensional problem? And the answer is pretty intuitive, really. You can do it whenever the heat is flowing overwhelmingly in just one direction. A perfect example is a window pane on a cold day. Almost all the heat is moving straight through the glass, from the warm room to the cold outside. Sure, a tiny bit of heat might move sideways along the glass, but it's so small compared to the flow going straight through that we can just ignore it. And that makes our lives so much easier. All right, so we've got our building blocks, time and space. Now we're ready to look at the master equation itself, the mathematical recipe that, when we use it right, can predict the temperature anywhere at any time. Okay, deep breath. Here it is in its one-dimensional form. Now, I know it looks a little intimidating with all the symbols, but trust me, it's built from simple ideas. Each little piece just tells a part of the story. You've got a term for how heat conducts through the material, a term for any heat that's being generated inside, and a term that describes how temperature changes over time. That's it. But the real beauty of this equation is how we can simplify it. If we assume we're at a steady state, poof, the time term just goes to zero and disappears. If we know there's no internal heat source, like in a simple wall, zap, the generation term is gone too. Suddenly, our big, complex equation boils down to this incredibly simple result. Now that's something we can work with. But let's add one of those pieces back in, heat generation. The key thing to understand here is that this is heat being created inside the object itself. It isn't flowing in from the outside. It's like having millions of tiny furnaces firing up all throughout the material, converting some other kind of energy into heat. And you see this happening all over the place. Those glowing red coils in your toaster, that's just electrical resistance creating heat. The immense power coming from a nuclear reactor, that's heat generation from nuclear fission. It can even be something as simple as sunlight being absorbed by a lake, warming it from within.
So we've got our governing equation, whether it's the full version or a simplified one. But on its own, it's just a generic template. To solve a real problem for a specific object, we need to give it some rules. We call these the rules of the road, or more formally, the boundary conditions.
I mean, think about it. The solution to our super simplified equation is just a straight line. But which straight line? There are literally infinite possibilities. To pin down the one and only correct answer for our specific wall, we have to know what's going on right at the edges, at the boundaries. The easiest rule you can set is just to specify the temperature directly. For instance, we might know that the inside surface of a wall is being held at exactly 120 degrees Celsius. Bam, that nails down 1 point on our temperature map. It's a fixed anchor. Another way to do it is to specify the heat flux. So maybe we don't know the exact temperature of a surface, but we do know that an electric heater is stuck to it, pumping in a steady 700 watts for every square meter. This doesn't fix the temperature itself, but it tells us the slope or the steepness of the temperature graph right at that boundary. Now, a really important special case of that is a perfectly insulated boundary. Here, the heat flux is just zero. No heat can get in or out. And what does that mean mathematically? It means the temperature gradient, that slope we just talked about, has to be zero. The temperature profile has to flatten out completely right at that edge.
And this leads to a fantastic little engineering trick. If you have an object that's perfectly symmetrical, like a big slab being heated the exact same way from both sides, that center line behaves exactly like a perfectly insulated boundary. Think about it. Why would heat need to cross the line of symmetry? It wouldn't. This beautiful insight means we can often just analyze half the object and cut our work in half.
Equation, boundary conditions, we have all the pieces. So let's put it all together and actually solve the puzzle, going from the general physics to a specific numerical answer.
Here's our problem. We've got a simple wall. It's 0.2 meters thick. We're going to assume it's a steady 1D problem with no heat being generated inside. So our equation is the simple one. And we know the boundary conditions. One side is held at a toasty 120 degrees Celsius, and the other side is at a cooler 50 degrees. The mission, should we choose to accept it, is to find the temperature at every single point inside that wall. We already know that for our simplified equation, the general solution is a straight line. We can write it as T of x equals some constant. Let's call it C1 times x plus another constant C2. The big question is, what are the values of C1 and C2 for our specific wall? Well, we just plug in what we know. We plug in our boundary conditions. We know T is 120 at x equals 0, and T is 50 at x equals 0.2, and we can solve for those two constants. And there it is. We get a specific, powerful, predictive formula. We can now tell you the exact temperature at any point inside that wall. We've gone from a general physical law to a practical, problem-solving tool. And look, this is so much more than a textbook exercise. This exact process, taking the master equation, simplifying it, and applying the right boundary conditions, is how engineers design everything from the processor in the phone you're holding to the heat shields that let spacecraft survive re-entry. So take a look around you. That laptop, that window, that mug of tea, they're all just heat conduction problems waiting for you to map their temperature.